So this presentation is on the continuing relevance of lead-based batteries, evaluating traditional technologies and the emergence of lead-carbon solutions. We'll be looking at one of the reasons why we decided to have this presentation was because recently we have been doing a project on lead-based batteries, and I think it's there's a misconception that lead-based batteries are going obsolete. No? So one of the motivations for this presentation is to show why lead-based batteries are here to stay. Specifically, recent technology or modification of the lead acid, which is the lead carbon battery. Okay, so just to give a quick introduction on different battery types, we have different types of applications for batteries nowadays. We have the stationary applications where we use batteries for solar PV systems. We have automotive, as we all know. We use batteries for electric vehicles, and of course our handheld and portable devices. So we have batteries used in cameras and our smartwatches and so on. Okay, so the focus of the discussion today would be on rechargeable batteries, not the primary but secondary type of batteries. And in different applications, the choice of chemistry depends on the density, the cost, environmental impact, safety, and application requirements. Okay, so the two popular technologies right now would be the older one, which is the lead acid, and fairly recent, not really new, the lithium batteries. As we all know, lithium batteries have been very popular, and I think this technology is here to stay, for even if we have been hearing news of scarcity in raw materials. The projection of the use of lithium batteries would be well into the 2050s. Okay? Lead acid, on the other hand, even though if it's an old technology, if you notice, our starter batteries in our vehicles have still been using lead acid, even though there are some lithium that's already being used in some vehicles. Okay, so I think one of the main reasons why lithium cannot really replace lead acid in everything is because of the safety issue. Okay, cost is definitely very relative. Cost can go up depending on the demand. Cost can go down depending on the supply and the demand as well. But one of the selling points for always going back to lithium, to lead, is the safety concern because of the risk of thermal runaway and overcharging. Okay, so even if we use them in our laptops and smartphones, we use them in our electric vehicles too. As you can see here, these are examples of battery failures for lithium batteries. So, now this one is a recent incident involving lithium. This happened about 2 weeks ago. Actually, it's if you look at the image on the right, they were already using an extinguisher for the batteries, but this is a screenshot of a video where you can see the lithium batteries just catching fire without any external, what do you call that? Without anything touching, essentially, the lithium battery. It was just there for storage. And this is an example of how high the risk is for lithium batteries. Okay, so it just caught fire, and there were 23 people who died, and I think about 20 who are severely injured. Okay, so this is lithium plant in Korea. Okay, so a few weeks ago. Okay, so lead-based batteries. We have been using lead acid for a long time, for more than 100 years now, since the first electric car in the late 1800s. They are relatively simple energy storage devices based on the lead electrodes. And the problem with this is that they have lower energy densities compared to lithium batteries. Okay? They have lower cycle life, primarily because of the sulfation in the negative electrodes. And this would limit the number of cycles, especially in heavy-duty applications. So the question is, will lead acid die or is lead acid dead? And why still choose it? So some factors would be cost effectiveness. It's still cheaper than lithium. It's well established. It is robust and safe. Actually, you can. It doesn't mean that the batteries will not fail. Lead acid can still have failures, but it is not as bad as the failure of the lithium batteries. So recent developments would be advancements in the performance by adding carbon in the negative electrode. Okay, so this gave rise to the lead-carbon batteries. They would still have the lead oxide in the positive electrode and activated carbon in the negative electrode. So this is the same technology used in supercapacitors. So this addition to the lead-based battery actually prevents the sulfation in the battery. So this would enhance the performance, the overall performance of the battery. It improves the cycle life. It improves the overall discharge and charge characteristics of the battery. So these are just some curves from a 24 ampere hour lead carbon battery. If you look at the image on the right, the capacity as a function of discharge rate. So technically, if you will compare, I forgot to add the performance of lead acid. So for lead carbon, if you look at the capacity here, we discharge the battery at a 10-hour rate all the way to 1 hour. Okay, so 10 C over 10 all the way up to 1 C. And if you will compare this to lead acid, at 1 C discharge rate, meaning you discharge the battery, if it's 24 ampere hours, you discharge it at 24 amps. At that rate, the capacity you will get is actually already going to be about 50% of the rated capacity for standard lead-acid batteries. If you look at the numbers here, the 24 ampere hour battery actually still gave us 20 ampere hours. Okay, so 20 ampere hours is ilang percent ba yun? Around a little over 80%. No? So it's a lot better than lead acid. So this just shows that it's very similar to different types of batteries. As you operate at a higher temperature, capacity goes up. Lower temperature, capacity goes down. So this is similar to other batteries. The one on the right is the cycle life as a function of DOD. If you look at lithium batteries, you would normally be using them up to about 80% DOD. For lead acid, the recommendation is about 50% DOD. And if you look at the lead carbon, the recommendation is to about 70% DOD. So 70% DOD means you can discharge it way further than the lead acid, and it is very close to the recommended operating mode of the lithium. But if you look at the performance, actually, Here, at 100% DOD, you can still get around 800 or maybe 900 cycles, which is way better than what you would get in lead acid. Okay, so this is actually already close to how, well, not really close, but it's nearer the performance of lithium. It's farther away from lead acid. So self-discharge rate is basically what the capacity of the battery would be if you do not use it. You just leave it on the shelf and then you pick it up again after some time. So it's just better. It's not as good as lithium, and it's a little bit better than lead acid. But there's a big difference between how lead-based batteries are stored. Because when you leave lead-based batteries, you do not want to leave them unconnected. Unlike a lithium-based battery where if you fully charge them, you would want to disconnect them because it will decrease the life of the battery, which is similar to cell phones, right? So if you fully charge your cell phone, you do not want to leave it connected to the charger. You have to remove it from the charger. And lead-based batteries would prefer to operate at a floating voltage. So this is why, even if you have this characteristic in stationary applications, the lead battery would always be connected to some power source, whether it's solar or some trickle charger is connected to the line or to the generator. Okay, so cycle life at different levels of DOD. Okay, so lead acid here, it's really very low. That's less than 1,000 cycles. Lithium, this is really highly theoretical. So, wala namang gumagamit unang-una ng lithium at 40% DOD. And wala pa nakakapag-prove na umabot ng 12,000. But this is a projected cycle life. Okay, so essentially, if you look here, they are very close to each other. Okay, so the lead-carbon battery at around 70% is somewhere 2,000 something cycles, and the lithium is about 3,000, or maybe 3,000 thereabouts. Okay, so what's the difference? For the lead acid, 500 to 1,000 cycles. Lead carbon is 1,500 to 2,000. Lithium is 2,000 to 3,000. Recommended DOD is 50%, 70%, and 80% respectively. Specific energy is 30, 40, and 128. Okay, so which is why the lead-based batteries are not really recommended for mobile applications. So they're really good for stationary applications because you don't want to have a very heavy battery for mobile applications. Efficiency, 70 to 85, 90, 90 to 95. Cost, the lead carbon is somewhere in between. Recyclability, this is where you have a very good performance from the lead-based batteries because they can be recycled up to 98%. Okay, lithium-ion is recyclable, but the problem is there's no critical mass right now. So it's very expensive to set up a recycling plant for lithium-ion, and but well, probably one day we will get there. Okay, so safety, generally safe for the lead-based, and lithium, you always have that risk of thermal runaway. So some notes for the conclusion. Lithium batteries are known for their superior energy density compared to other technologies, but they are still relatively expensive, face challenges with raw material scarcity, and might be excessive for applications where high performance is not a critical requirement. Lead-based batteries, including lead acid and lead carbon types, are still suitable in applications where weight is not a primary concern, and lead-acid batteries are still the most cost-effective option for rechargeable applications that do not demand high performance. And lead-carbon batteries represent a significant improvement over traditional lead-acid batteries in terms of cycle life, cycle efficiency, and state of charge. while retaining the robustness of lead-acid technology. Thank you very much.
Thank you, Dr. Odulio. Are there any questions from the audience? There's one question, sir.
Earl Wanico po from UPD Lithium-ion program. I just want to ask, I'm curious about kasi carbon, I think, has already been used even sa zinc carbon batteries, which have been around earlier than lithium-ion batteries. So I saw kasi the references na nandun sa footnote, 2022. So why only now that carbon has been integrated with lead-based batteries, why not earlier? So any motivation or any development?
As to why, I don't know why really, but the infusion of carbon, I think, dates back to 2017. That was the first time I saw it used in lead acid. And it had a good performance, but I think one of the reasons that it really did not take off was because lithium was really the more popular battery at that time. No, actually, the company that started this in 2017, binenta nila yung technology. So they closed shop and they sold the technology or the rights to someone else, and someone else is using that in the manufacturing yung lead carbon. No? So I really cannot say kung bakit hindi before that. But yeah, it's not really 2022 when they started, but almost around 7 years ago. Maybe even before that, no, for R&D.
One last question. Where do you see the future of lead carbon batteries, like especially in battery energy storage systems? Kasi halimbawa, if EVs will be rolled out eventually, there needs to be charger along the highways like NLEX or SLEX. But these are far away from the cities. So do you see a future for lead carbon batteries in, I don't know, microgrids where, you know, they are isolated areas, but you still need some charging going on? Maybe if it's integrated with solar or other types of energy harvesters?
I think lead carbon has potential future for solar PV systems. We are going to deploy lead carbon in a project that we are doing right now for solar PV. Okay, there is also a plan to do it for e-trikes and two-wheeled electric vehicles, but I am not very excited about that simply because of the weight problem. Okay, you can use it definitely, but I think the future of lead carbon would be to replace technologies for stationary applications. So there is a good chance na may potential siya sa stationary applications.
Thank you po.
Thank you. Thank you.
Are there any other questions for Dr. Odulio? Okay, if there are none, I would like to give this certificate of appreciation to Dr. Carl Michael Odulio for sharing their invaluable insight and work on the continuing relevance of lead-based batteries, evaluating traditional technologies, and the emergence of lead carbon solutions during NEECECON 2024. So I would again like to thank the presenters for their presentations and their answers to the questions. I hope we all learned today about the newest academic and industrial development in electric vehicles and energy storage systems. Hopefully we can all participate again tomorrow. So before we go, I would like again to extend our heartfelt gratitude to Advanced Energy, Techmark Keysight Technologies, Embedded Silicon Technology Solutions Corporation, Meralco, Analog Device Incorporated, Presidium PH Corporation, Road and Schwartz Philippines Incorporated, Alexan Commercial, Maker Lab, Samsung Electronics Philippines Corporation, and Challenge Systems Incorporated for their invaluable support to the NEECECON 2024. So again, I would like to thank you all for participating, and I hope we can all participate again tomorrow. Thank you.